So next, we're going to draw a table. So it's going to look like this. So we'll draw a vertical line and a horizontal line. Now, for the rows, we're going to take each of the factors that we had in our f prime of x once we factored it completely. So 12x is one factor, x minus 2 is another factor, and then x plus 1 is the third factor. So each one of those factors is going to get its own row. So 12x will be the first one, then x minus 2, then we'll have x plus 1, and then the last one will be the product of all three, which was f prime of x. Okay, so those are the rows. And then for the columns, we're going to have one line down here for each of our critical numbers. So remember what they were? Well, just check on the previous page, right? We had -1, 0, and 2. So make sure you put them in order from least to greatest. So -1, 0, and 2. If I change the order of these, it wouldn't work very well or at all. So make sure they're in ascending order. Okay, and then now, this is just going to be like solving a nonlinear inequality. We did an example of that in section 1.1. So if you think way back to then, we're going to follow the same sort of approach. The idea is now we're going to select a sample point in each one of these corresponding regions. So here I want to pick a number that's less than -1. But I want to pick simple numbers. Keep it as simple as you can. Avoid fractions if possible. But if you can't avoid fractions, that's okay too. You have to use them sometimes. Like for between -1 and 0, let's do -1/2. And then between 0 and 2, well, probably the simplest choice would be 1. And then something greater than 2, how about 3? Right? Anything greater than 2 would work just fine. Okay, so then plug those into each of these three factors and determine their sign. So if you plug in -2 to 12x, you get a negative. And if you plug it into x minus 2, you're going to get a negative as well. Plug it into x plus 1, -2 plus 1 is -1, right? Just take this number and plug it in for x for each of those factors and just record the sign. You don't need to record the actual value. You just care about the sign. Okay, and now the product of three negatives we know is going to be a negative. So we know the sign of the derivative on the interval of points that falls less than -1. So between -infinity and -1, that's really what interval this is. But f prime of x is negative on that interval. So now do the same thing with -1/2. Plug -1/2 in for x. So we'll have negative, plug in for x here, you're going to have negative again. But then when you plug it into x plus 1, you get -1/2 plus 1. That actually works out to being positive. So the product of all three of those factors, a negative times a negative times a positive, is going to be a positive. Okay, what about the +1 now? Plug that into each of those three factors. You're going to get plus positive when you plug it into 12x. You'll get a negative if you plug it into x minus 2. And then you'll get a positive if you plug it into x plus 1. So positive times a negative times a positive, those three factors multiply to give you a negative now. And then lastly, when you plug in a 3, you can check that all three of them are going to be positive. So therefore the product, f prime of x, is also positive. So if you apply now the increasing-decreasing test, this is going to answer the question for us. Because let's take this interval, for example, the interval between -infinity and -1. F prime of x is negative on that interval. So by the increasing-decreasing test, take I to be the interval that goes from -infinity to -1. Since f prime of x is negative on that interval, then the function is decreasing on that same interval. And you just and the same for the other three intervals. Let's do one more, just in detail. From -1 to 0, f prime of x is positive between -1 and 0. So on the interval of points, take I to be the interval -1 to 0. F prime of x is positive on that interval, so therefore f is increasing on that interval. So you're just applying the increasing-decreasing test to each one of these columns, essentially, because they really represent intervals. Okay, so we can finally finish this off. We can say, therefore, f is decreasing on -infinity to -1, and it's also decreasing on the interval between 0 to 2. So just to make our answer as concise as possible, it's decreasing on this interval, and it's also decreasing on the interval between 0 to 2. But it should be understood that it's not technically decreasing on the whole set. necessarily. It might be, but we don't know that for sure. But what we do know for sure is that if you look at each of those intervals by themselves, like f is definitely decreasing on this interval, and f is definitely decreasing on this interval. But just to make it so that our answer is not too long-winded and we don't have to keep writing out long sentences to describe everything, we can use the union notation to express that. So it's decreasing on this interval and it's decreasing on this interval. That's what we mean when we write this. And then for the other half of the story, f is increasing on the other two intervals. It's increasing on the interval between -1 and 0, and as well as the interval 2 to infinity, right? This is 2 to infinity, just everything greater than 2. And this was 0 to 2, or pardon me, -1 to 0. So those are your intervals, and now we got everything, right? We know when f is decreasing and when f is increasing. And that's what was asked for. And this leads us now to our next question. It was, well, what about the local extrema? Can we get the local extrema out of this? And the answer is yes. In fact, we have all the information now to identify the local extrema. And you might already be able to guess how we're going to do this, but just in case, we're going to go through it in detail. This is called the first derivative test. This is really the test that allows you to take this information and determine, okay, well, where are the local maximums and where are the local minimums? Okay, so let's go through this carefully. So start with, you got a function f, and this applies to continuous functions, by the way. So you've got a continuous function f, and you've got some critical number of the function. Call it c for the moment. So the first part of the test says that if, by some chance, your derivative changes from negative to positive directly at that critical number, if that critical number happens to be the point where the function's derivative changes sign, in other words, to the left of c, for numbers slightly smaller than c, f prime is negative, but for numbers slightly greater than c, f prime is positive. That's what it means to change from negative to positive at x equals c. If that happens, then you've got yourself a local minimum at x equals c. So f of c is a local minimum. But if the sign change happens in the other sense, so if f changes from f prime changes from positive to negative at x equals c, so for values of x that are slightly smaller than c, f prime is positive, but for values of x that are slightly greater than c, f prime is negative. That's what it means to change from positive to negative. If that happens, then f of c is a local maximum. You've got yourself a local maximum for the function right at x equals c. So, and we have enough information. In the previous example, we have all the information that we would need to make those observations contained in this table. So let's actually the next example, it's the exact same function, but now we're asked to find all local extrema of this function. So if you see a question like this, typically what you're going to do is you're going to jump right into what we did at the very beginning of the previous example. You're going to, the first question you want to answer is this one. When is the function increasing and decreasing? Because if you can answer that question, and it's a continuous function, you can determine where all the local maximums and local minimums are. So this is what you would do at the beginning. But since we've already done it, we've already found the critical numbers, we've already found the intervals on which our function is increasing and decreasing, we can just carry on from that. Okay, and the way you'll do that, this is the table I like to draw because it really gives a nice visual sense of what's actually happening. So I like to write f dt, and it stands for first derivative test, because that's what we're applying here. And you can also think of it as the first derivative table, because that's what this table really is. It's going to have two rows, one row for the first derivative, f prime, and one row for f. Okay, and so we're going to do one slice down for each one of the critical numbers. So we had -1, 0, and 2. Those haven't changed. And then now, just take the bottom row of our previous table. This negative, positive, you can forget about the rest because we don't need that information anymore. So we can fill in the f prime row just by copying this row, negative, and positive, because the dividing numbers, -1, 0, and 2, those are the same down here, -1, 0, and 2. So we have negative, positive, negative, and positive. And the point is, whenever the derivative is negative, the increasing-decreasing test tells you that the function f is decreasing. So I just like to draw a downward arrow to indicate that. Okay, so, but then when it's positive, if f prime is positive, the function's increasing. And then when f prime is negative, now the function's decreasing again. And then when the function's derivative is positive, the function's increasing. So this gives you a little bit of an idea of the shape of the graph of f. It's going to decrease, then increase, then decrease, then increase. It's a crude illustration of how the graph works. It doesn't actually tell you exactly how the function behaves by any means, but it does give you a sense of its shape, at least to a rough degree. And it does tell you, you can imagine here, if it's decreasing, then it increases, you're going to have a local minimum here. And if it's increasing and then decreasing, you're going to have a local maximum at x equals 0. And then if it's decreasing here and then increasing, you're going to have a local minimum at x equals 2. Really, that's what this first derivative test tells us. If f prime changes from negative to positive, like it does here, right? It changes from negative to positive at x equals -1. Think of the -1 as your c value. The test says that f of c is a local minimum. So really that's saying f of -1 in this case is a local minimum. And then similarly, the part B of the first derivative test, you've got f prime changes from positive to negative right at this point, x equals 0. So think of 0 as your c in the second statement. And this tells you that f of 0 is a local maximum, which kind of agrees with our table, right? If it's going from increase, if the function increases and then turns around and goes back down, that means you have a local maximum here. So that's why f of 0 is going to be a local max. So really all that's left is just to work out what the y values will be, because these are the locations of the local extrema, but it doesn't tell us the actual values. So we should plug those into the function to figure out what they are. So let's evaluate f of -1. So if you plug -1 into f, you're going to get 3 times -1 to the 4 minus 4 times -1 to the 3 minus 12 times -1 squared. I'm just plugging -1 in here, right, and then plus 5. So what you end up getting here, if I clean up some of the brackets, -1 to the 4 is just +1. So this will just be 3. -1 cubed is -1. Multiplied by -4, you get +4. So it's 3 plus 4. -1 squared is just +1, so this is going to be minus 12, and then plus 5. Okay, so this is 7. 7 minus 12 is -5, but then you add 5 and get 0. So f of -1 is 0. And then just work out f of 0 and f of 2 in the same way. So f of 0 is going to be 3 times 0 to the 4 minus 4 times 0 cubed minus 12 times 0 squared, which is equal to 5. So these three terms are just going to be 0, right? So you're just going to end up with 5. And then our last point, plug in 2. So f of 2, plug 2 in for x, so we'll get 3 times 2 to the 4 minus 4 times 2 cubed minus 12 times 2 squared plus 5. So work everything out. 2 to the 4, that's going to be 16. So we got 3 times 16, that actually works out to 48. 2 cubed is 8, so we got 4 times 8, which is 32, so you get minus 32. This will be 2 squared is 4 times 12 is 48, so we got minus 48, and then plus 5. So the 48's cancel, really, and we get negative 32 plus 5, that'll be negative 27. Okay, so that's what we get for f of 2. So that's how we can answer the question now. So let's finish it off. So let's put our conclusion down here. Therefore, let's state the local minimums first here. F of -1 and f of 2 are both local minimums. So we'll say f of -1, which was equal to 0, by the way. Right? This is our way of giving all the information to the reader in one place to summarize it all neatly and concisely. And then they can look back at our work if they want to see the details afterwards, but they shouldn't have to. They should never be forced to now scan through our work to figure out what our conclusion was. Then if they have to, then we haven't done our job, right? We've just left that work for them to do. So let's say f of -1 is 0. That tells us the location of the local minimum is at x equals -1, and the actual local minimum itself was 0. That's what this local minimum is. Now over here, we've got f of 2, which worked out to be -27. Those are the local minimums. And then for our local maximum, it's going to happen at 0. So let's say f of 0, which worked out to be 5, right? So we got f of 0 is equal to 5. That is the local maximum. And then that's all the information summarized at the end. That's how you want to finish these problems off. So the first derivative test really sums this up. But the process for finding local extrema for continuous functions is you want to find your critical numbers, and then you want to determine on which intervals is the function increasing and decreasing. So find the critical numbers and use them to set up this table. And then once you have this table, you don't have to bother doing this. If all you're asked for was the local mins and the local maxes, you don't have to explicitly state this, because it's really the information is right stored neatly in the table. So you can just go right from the table, and because if this is what you're asked to do, find all the local extrema, you're going to jump right into this. And sometimes what you might do is you might even just say, well, rather than doing a separate table, why don't I just take this bottom row here and just append it onto this table. I'll just draw one more line across and add another row for f of x, and then fill in the decreasing, increasing, decreasing, and increasing. Save yourself a little bit of time to just do it all in one pass. That's typically what you do, but this was broken up into 2 separate examples. But in general, the questions you would expect to see are going to be functions or problems like this in practice. You're looking for the local maxes and local minimums.